Okay, so welcome back everyone. Today is Wednesday, May 19th. Okay, so we are going to start doing the lecture of ES201 solid mechanics. Okay, so there is no new announcement today. Everybody turned in syllabus, looks like. So right now, if I look at your score, I cannot show you this, but I can show right now here because at the very beginning of the semester, everybody is 100% A. Because you turned in syllabus, you earned 1 out of 1. So far, it's 100% A, so I hope you keep it. Okay. Anyways. So probably the next one to come will be the homework. Homework of section 1A. I'm going to announce it whenever I know it. It's going to come soon. Okay. But the day you turn in your homework will be the day you take the quiz. Quiz will be, like I said, in class, last 10 to 15 minutes, crossed book notes, very similar problem. One problem, single problem will be chosen out of either homework or class example, something very, very similar. So if you spend your time doing your homework, it should be very easy quiz. If you don't do such a thing, this is a nightmare quiz. You can never figure things out in 10 minutes in class, okay? So be prepared for it. So it is very, very important. Number one, you have to do your homework all by yourself, figure things out. It's okay to ask questions. I'll be happy to answer anything, but don't ask me simply because you don't want to think, you don't want to spend time, you don't want to figure it out. That's why, hey, let's ask professor. That's a lazy question. Okay, I still answer that question, but my attitude could be nasty. I don't know. Okay, you can try. I'm not tutor, and you don't need a tutor for this class. Okay, so important thing is pace yourself every day. You have to do something from today. Okay. Do you have any question before we begin today's lecture? If you're all good, please react on something. Good, good, good. Appreciate that. Okay. By the way, yesterday's lecture is already posted here. So if you want to listen to yesterday's lecture, you just simply click here. Okay. All right. All right. So I'm going to go back to the note. So let's begin with section 1A, Introduction to Engineering Mechanics. Okay. So Unit 1 is all about Introduction to Engineering Mechanics. Okay. So now this unit and section 1A, I'm going to cover 5 subject matters. Introduction to Engineering Mechanics, scalars and vectors, vector operations, vector addition of forces, addition of system of coplanar forces. Just a few memos here. Okay. So basically those are something called vector calculus, right? Okay. Does anybody know the meaning of coplanar? Please speak up. Please speak up. Wrong answers welcome. Welcomed. What is
Is it
coplanar?
a is it a multiple plane?
Coplanar means on the same plane. On the same plane. That means coplanar is a 2D. So if you say multiple planes, it's going to be 3D. So if you look at 3D, you have to do a very good sketch, of course. Coplanar is, wait a minute, am I right? I don't know. Let's find out. Let me just take a sneak preview. What is 1.5? Yeah, coplanar is 2D. Looks like, yeah, everything's 2D. See that? Yeah, okay. So everything is xy plane. Ah, all right. Good, good, good. So we are going to begin with two-dimensional vector subtraction, addition, or combine two vectors, three vectors, finding out the result, or resolve one vector into two directional components, stuff like that. We're going to do that to begin with in 2D. And then we are going to extend it to 3D. Okay. All right, good. So I was right. Good. I appreciate your comment. Wrong comments also appreciated. Okay. What is the worst thing you can do for this type of lecture, especially online remote? Okay, you just log in, go somewhere else. You just pretend like you're participating. That's huge waste of your tuition money. Don't do that. Although if you choose to do that, I cannot stop it. What is the best thing to do? You just to participate, no matter what. Okay, you speak up, react, take good notes. If you don't understand, ask questions. Okay, anytime. All right, so take a look at page 2. So let's just to begin discussion with Introduction to Engineering Mechanics. What is engineering mechanics? This is engineering mechanics class. What is engineering mechanics? Anybody? Where does that term come from? What are those classes you're talking about? You know, oh, this is engineering mechanics class, ES class. This is ES201 statics. This is the very first engineering science class that you take. After this class, what you're going to take?
Solid mechanics.
Solid mechanics. ES.
I think we actually take dynamics after statics.
After statics, dynamics. ES202, well, actually, everything is required for everybody, but depending on your track, some classes are essential, some classes are, yeah, kind of important, but it's not quite. If you're aero track, obviously, you are forgetting something. Aero track people, raise your hand.
Fluid mechanics.
Fluid mechanics. Here we go. There. So this is something super important, okay? If you're aero track, oh my goodness, you have to master this class, otherwise you'll be dead. I mean it, okay? Lots of people actually take this class. Oh yeah, you know, I'm coasting through. I kind of took the class, then take my aero class, burn. Oh my goodness. Don't be one of those people. This is important class. Now, if you are astro track, obviously this is, man, this is very, very important. I don't know who's teaching this class, but depending on who's teaching, this class could be a nightmare, right? I'm not gonna name who. Dr. W. Anyways. This is a solid mechanics. This is a very basic class for structures. Who's teaching structures? Dr. L, right? Yeah, I'm not gonna name. But anyways, those are tough classes. In other words, how much time you are willing to spend for those basic classes will determine your future fate. People say, hey, those are gauntlets, you know. Tough classes. No. Tough things come later. If you take care of those classes right, those tough classes will become all of a sudden your fun classes. You fully enjoy being an engineering major. Graduate, get a prestigious job, enjoy your life. I hope that's what you want. Okay, so don't listen to what the fake news said. Well, fake news, I shouldn't say fake news, but the fake like information that the students, you know, spread over. Oh, you know, don't take Dr. W's class. Well, it's a nightmare class. Take this teacher instead. He's easier kind of information. That's a BS, okay? If you say, well, Dr. W is so difficult, tough, and nightmare crust, that is a very good indication that you'll be educated very, very well. Anyways, so this course ES201 is the beginning of those. Welcome to engineering core curriculum. But you have to go through it to be your major classes AEs. You can never go to those level unless you go through those engineering core majors, engineering science, engineering mechanics. Actually, engineering science isn't. ES is engineering science. What is engineering science? What is the difference between engineering mechanics? So this science terminology comes into play because this is physics of why this happens. So depending heavily on physics, in other words, theoretical, you have to understand theory first before you understand mechanics. Okay, engineering mechanics is usually used mainly for like structural analysis. Structural analysis is engineering mechanics. In other words, you're going to build something, making a metal plate or something as a skin of an airplane, and then you want to make it strong enough but light enough so that airplane can still fly but still in one piece. And then how fast can you go, kind of thing. You have to figure those important and yet difficult, challenging subject matters. That's called engineering mechanics. That requires physics, basic understanding, theory. Of course, physics uses math, but math is not that important. You already know math. You use the math, okay, to analyze in physical sense. And then in the future, before you graduate, you're going to actually design something. That's mechanics, okay? Everything is accumulative. It's not going to happen overnight. So just don't think rightly, oh, this is a class I can kind of sit back, relax, and have a coffee and don't pay attention. I can go through and no, you're going to spend 4 years with serious hard working. Try to understand the concept. Okay, so question here. Number one, statics is a fundamental course, focuses vector analysis and rigid body in equilibrium are two very important terms. Let me underline. Vector analysis is fine, but rigid body, equilibrium, two important things. Rigid body, of course, you know that. Rigid body is a very hypothetical thing. It doesn't deform at all. No matter how high you apply the external force, this thing doesn't deform. That's rigid body. Idealize the concept. We are going to deal only with rigid body in statics, okay? And equilibrium. What is equilibrium?
No acceleration.
No acceleration is 70% correct. 30% wrong means in order to have acceleration, you have to have a motion. Equilibrium is, okay. Constant speed could be also sometimes considered equilibrium. So you're right. But in statics, as the name implies in this particular class, basically no motion. Okay. If you have a motion with a constant speed, if you choose a carefully proper coordinate frame, you can consider that as an equilibrium too. Okay, but let's just for a moment, no motion. Okay, what causes no motion? Suppose if you're pushing something and moving around, I have a mouse moving around, it's moving. I'm applying the force. What makes it no motion?
When you have no force?
No force is one thing, but suppose if you apply one force, can you still, one or more forces, can you still create the no motion condition?
No.
If the
If you
net forces cancel, it's in equilibrium.
Oh, yeah. So net forces, that's quite important. If you apply force here, apply force equal and opposite, it's balanced up, so this microphone doesn't move. So let's just write it down. Conditions that actually occurs, okay? You apply force, but you apply multiple forces. Could be 2, 3, 4, 5 forces, but as a result, you basically balance up each other so it doesn't create any motion as a result. And then not only forces, but you can also apply moments. Do you know moments? Sometimes called torque. Moments applied on a body. Body is a rigid body. Condition that forces and moments applied on a body completely balanced. As a result, there is no motion. This is called equilibrium. So statics in this class is all about rigid body in equilibrium. Okay, so that's the baseline concept. Now, you're going to take solid mechanics after this. What is that class is all about? I don't know who's teaching, but you're going to take solid mechanics. What kind of class is that after this class? Ryan, go ahead.
The study of deformable bodies. So
Deformable body,
strict.
yeah. Oh, so solid mechanics is basically about the same as statics. The only difference is body is now deformable. Okay. If you're dealing with deformable body, what happens is when you apply the force, okay, the body deforms. As a result, you're going to develop internal strain. As a result, you're going to have internal stress also. You're going to deal with that. That's the solid mechanics. But the starting point is the statics. Okay, so here's important thing. Okay. If you don't have a rock solid foundation for statics, there's no way you can solve anything in solid mechanics. I've been teaching solid mechanics. Well, actually, I taught solid mechanics about 5 years in school that I was doing graduate program. I was a PhD student in teaching solid mechanics. You know, over and over and over, students try to take solid mechanics without having solid understanding of statics, and then it's impossible. Okay, so be careful about that. Solid mechanics is impossible unless you understand statics, because essentially it's the same engineering mechanics. You're now dealing with soft body that actually takes the force and then deform and then develop internal stresses. That is all about solid mechanics. Okay, dynamics. Okay, what is that all about?
With motion?
With motion, yes. So dynamics, you are not going to talk about, okay, the deformation of a body. Still a rigid body. However, if the rigid body is in motion, okay, suppose if you apply force and then body starts moving, it could accelerate in certain direction. What is the behavior of that? Okay, so those three are essentially same category of engineering science courses. We are just constrain one condition and then simplify and analyze. So again, as you go through those classes, you need to systematically understand what aspect of engineering science we are dealing with. Those are not independent classes. Those are closely related. Now, here's something nobody will tell you to do, but I will tell you. After you take all those three classes, you have to integrate and make it summarize and then have a big blue picture. In other words, small tiny pieces of puzzle, you have to put it together by yourself. People actually do that without consciously thinking about. But that's what you need to be doing. Students sometimes struggle to do that. Okay. In upper division classes, sometimes students just cannot perform well on any engineering class you take. Those are the students actually cannot piece together those things as a big picture. Okay, so statics comes in, dynamics comes in, and then thermodynamics comes. Those are not independent classes. Those are basically closely tightened up together. You have to piece together by yourself. Nobody actually tells you that, but I have to tell you this is important. Oftentimes students don't realize it. After you complete all of those core engineering science classes, you have to try to do piece together by yourself. I don't know what the method you are going to pick it up. You can possibly create one big file folders with all of those classes and homeworks and notes all combined, and then maybe, I don't know, tab it so that you can pick up any information you need for any upper division classes out of that file folder or something like that. Piece together, because this is a systematically speaking engineering science class. You need that for your major classes. Without those foundation, it's a joke. You take AE class in upper division. Anyways, so next page. Now in this statics class, okay, we are going to use idealized models. Something we have to idealize because we are dealing with a rigid body. So very first step idealization is, okay, so let's consider a particle. What is particle? Nobody knows. Okay, because it's idealized as saying it's a particle. Okay, so we are dealing with this particle. This has a mass, but the size can be completely ignored. It's small enough so that I don't care about the size. Okay, geometry of the body is not involved. So this is a particle. First of all, idealize the concept. Now, gradually, we are going to move into rigid body, which is some actual body. It could be a car body, it could be an airplane body, or whatever, what not to, but we are going to still consider its rigid body. It doesn't deform at all. So both idealized. We are going to deal with two different kinds of idealized thing. Then suppose if you're talking about a particle, oh, this is a particle. This is a very small, tiny thing, particle, okay? So this is a particle. Hey, let's apply forces, okay? Okay, I'm gonna apply this much force. I don't know, 200 newtons force here. And 50 Newton forces here. 250 Newton forces, I don't know. Hopefully those two combined together with equal and opposite 200 Newton. If so, it's equilibrium. I have no idea the angle is, but this 250 combined together is equivalent to this 200 Newton equal and opposite to the original 200 Newton. If so, this particle is in equilibrium because there's no motion involved. Okay? So I guess starting from there, so question is, okay, so what is the angle here? What is the angle there? That is going to be a problem, starting point for the statics class, okay? So before we begin such a thing, let's talk about very, very famous Newton's 3 laws of motion. Okay? This is first law, Newton's first law. A particle originally at rest or moving in a straight line with constant velocity, okay, will remain in the same state if the particle is not subjected to an unbalanced force. What do you mean? This is equilibrium. Here we go. Okay. Equilibrium. Newton's second law. A particle acted upon by an unbalanced force experiences an acceleration that has the same as the force and magnitude that is directly proportional to the force. F equal to ma. By the way, this is the governing equation of ES204 dynamics. Okay, this is the concept of this class, ES201, statics. Okay, Newton's third law of motion. The mutual forces of action and reaction between two particles are equal, opposite, and collinear. This is actually very, very important in this class. ES201. We are going to later revisit this concept. This is basically the baseline concept of support reactions. Free body diagram. Free body diagram is very important item in statics and also solid mechanics. Every problem, almost every problem you solve requires free body diagram. Let's say, for example, this is a bar or something. You are going to support it. This is a pin, the support, sometimes called. The other side is, I don't know, you put the roller on the ground. On the ground. Oh, let's analyze this. What is the first step you need to be doing? You have to draw free body diagram. We are going to cover that later. Don't worry too much about it. You are going to basically try to disassemble everything. Remove the pin. Remove the roller. And then replace with equivalent support reaction forces. So those are the two support reaction forces for the pin. So this is a single support reaction force replacing this roller. This is free body diagram. After you sketch out the free body diagram, then now you are going to apply equations trying to solve. Okay, so if you apply 500-pound forces here, what is the force reacted here? Stuff like that. Okay. Any questions so far? Please stop me anytime if you have any question. All right, next page. Newton's law of gravitational acceleration. This is based on second law because this is essentially force is created due to mass times acceleration. Now this acceleration becomes gravity. Okay. So this is entirely based on the second law of motion of Newton's. Okay. So this actually provides the important information of how much gravitational acceleration you're going to develop on the surface of a planet. Okay. So, oh, by the way, do you guys know the gravitational acceleration on standard sea level on Earth? G. Anybody?
Is it about 9.1 meters per second squared?
98.1, is it?
9.81.
9.81, sorry. 9.81. That's right. What's the unit?
Meters per second squared.
Meter per second square. That's correct. Anybody knows British unit, U.S. customary unit? People understand, you know, you love SI unit, but this is the United States. What is U.S. customary unit?
I think it's about
US is
32.
something like, sorry, 32.2
Oh,
per second squared.
okay, feet per second square. So, okay, this is the standard sea level gravitational acceleration on Earth. This is SI unit. This is US customary unit, British engineering. Okay. So it looks like you have two different unit system, huh? Yeah, too bad. I'm originally from Japan, you know. After I came to the United States, it was my first time looking at what is a pound? I've never heard of it. Why 10 inches and not one foot? Stuff like that. But we're going to cover that. Okay. So here's another question. What is the difference between mass and weight? Oh, do you guys know that? So I'm talking about here. This is a force of gravitation between two particles. Suppose if you're talking about weight of something. W. This is a weight. So let's just pick up this mouse. This mouse has a weight. I don't know how much pounds, but how can you determine such a thing? How much mass do you have for this mouse? Multiply by G, gravity. This equation comes entirely from here. Okay? So suppose you have two things. One is weight, one is mass. Are those the same thing or different thing? Of course, as it seems different. What is the difference? Okay. This is actually quite important discussion. So this is a joke, so please don't do that. But suppose if you go to shopping today, I don't know where, it could be Walmart, could be Rise. Go there and buy something. Let's say you buy a bag of apples, and then the bag says 5 pounds. Okay. Then bring that apple 5-pound bag. Go straight to the customer service. Ask this question. Is this 5-pound mass? Or is this 5 pounds of force? This is a joke. Don't do that. What's your response? Suppose if you have a part-time job at the customer service rep, a Japanese professor of Embry show up and say, hey, is this a 5-pound mass or 5-pound force? I want to answer. Well, how do you respond?
Well, mass can't be a force, right? So if you say 5 pounds of force, that doesn't make sense to me. Because pounds is, well, actually, no, that does kind of make sense because that's a weight.
Good. So you're saying this is 5-pound mass, huh? If I say
that's what I 5-pound mass doesn't make sense at all.
Okay, so this is 5-pound force, huh? If I say it, then
Right.
you're a customer service rep and saying, yep. Then I say, fine, I'm going to pay the money for this based on your statement saying this is 5-pound force. Is that correct? And then you say, yep. Go ahead, you're crazy. Then you're right. So is the 5-pound mass different from 5-pound force?
Absolutely, I would say, because a 5-pound mass isn't a thing.
Okay. So people oftentimes say 5-pound force. Have you ever seen this? And 5-pound mass. Have you ever seen this? Looks like two different kind of expressions. Are these the same? No, it's not the same. But suppose if I bring a 5-pound bag, is this pound mass or pound force? Then you go like, I don't care. You can take either way. That's correct. Okay. So we're going to discuss about that a little bit later. But those are different. Of course, one is mass. The other one is force. Force is created by mass. In other words, weight is a force. Okay. Weight of 5 pounds force can be created because you have a 5-pound mass of an apple under the gravity of Earth. Let me repeat once again, okay? You may be confused. So you pick up a 5-pound mass of an apple, okay? Bring it to the scale and drop it on the scale. What does the scale say? 5 pound. Oh, is that 5-pound mass you're measuring? Or 5-pound force you're measuring? Which one is it? You are measuring force because mass can never be measured. Force can be sensed because the force is the weight. Weight is the force created by the presence of gravity. If the original object have 5-pound mass under the standard sea level gravity of Earth, it should indicate 5-pound force over weight. That's something you are measuring. So does that mean, do I have 5-pound mass over apple? Yeah, if it's on Earth. Do you understand that? This is going to be most likely first quiz problem. Do you understand that? Okay.
Like the scale just takes into consideration the acceleration?
That's right. Because you can never measure directly, at least, the mass. Okay? Mass cannot directly be measured. So it's like how close those particles are packed together to create one apple. And that apple happened to be 0.5 pounds of mass. But how can you measure that? No way. You can never measure such a thing. This is the force or weight. Weight is a force. Can be sensed. In other words, the scale here is going to sense the force which is pushing the scale. This is the force. This force is created based on the mass of an apple under the influence of the gravity. So the apple is now creating the weight, which is a force, which pushes the scale. That's happened to be 5 pounds of force. Under the Earth's gravity, this apple have 5 pounds of mass. So you actually backtracked and detecting how much mass do you have under the influence of standard gravity. If you go to moon and create Walmart in moon, you have to redesign everything for that scale. Okay. Or actually, you have to always deal with, okay, how much pound mass do you have here? Is this pound mass or pound force you're talking about? Because those are not the same thing on moon. Why is that? Because the moon's gravity is not this value. So the same 5-pound mass on moon is not going to create 5-pound force of weight. How much do you think it's going to create?
Probably less because you're
Less.
multiplying by a
Yes.
smaller gravity.
That's right. Gravity of moon is 1/6 of Earth. So suppose if you have 6-pound mass of huge apple. Drop it on the scale on moon. It only shows 1 pound force. Okay, on moon. If you bring it back to Earth, it shows 6-pound force because it's 6-pound mass. Dropped on the scale, 6-pound force. But on moon, it only shows 1 pound force. Okay, so I hope you get the basic idea for that. Weight and mass are different, okay? So, that's right. So from the Newton's law of gravitational attraction, you're going to apply two different mass. One is the mass of a body, the other one is mass of the Earth. Apply this equation, it is going to create the equation of weight on Earth, okay? Equation of weight. Weight is equal to mass times gravity. Gravity in standard unit on Earth is given, standard sea level. I just keep saying sea level. What do you mean by that? If you go to higher altitude, this is going to change. Okay, so in space shuttle, in really high altitude, no, it doesn't have this much gravity. So how many people here are actually space track, astro track? Raise your hand. So too bad, you have to deal this all the time, okay? So mass is not equal to weight if you go to space because the gravity is not this value. So if you go to Walmart and do such a trick, oh, okay, this is 5-pound mass or 5-pound force, which one is it? And then people say, well, I don't care. You can take either way because this is on Earth, standard sea level. The values are the same. 5-pound mass of an apple create 5-pound mass of force. So you can either take pound mass or pound force. But if you do such a thing when you design spacecraft, what happens? You can tell, right? Okay, so let's be careful, especially if you call yourself Astro Trek. Differentiate pound mass and pound force. Okay. Oh, that's why I hate US customary unit. I love SI unit. Do you say that? Does anybody say, oh, I love US customary unit. It's better than SI, or SI is so good. I love SI. If you love SI, raise your hand. Two, three people, 4, 5, 6 people, seven people, 7 out of 9 people love SI. Okay. Oh, actually 8. So yeah, I can hear your feeling. 2 unit systems we have to cover here. Okay. 2 unit systems, SI, and then US customary. This is something called British Engineering Unit, BE. This is like a System International, something. This is French word, okay. International System of Unit SI. Let's begin with it, okay. So we are going to actually talk about three base unit. Actually, 3 base. I'm going to use the term dimension. So if you come to think about anything you use in engineering, okay, well, you can think about, well, what kind of things we're going to use to quantify, such as, okay, velocity, acceleration, weight, force, I don't know, lots of things. But those are essentially come down to 3 base dimensions: mass, length, and time. So those are the three base dimensions. Oftentimes, we're going to add theta, temperature. By the way, this is a Greek lowercase theta. Oftentimes, we use Greek words. I have to give you probably handout of Greek letters. But anyways, let me remind myself. Okay. I'm going to give you a handout of Greek characters, okay? So this is theta. Okay, so capital M signifies the mass, capital S ranks, capital T is the time. So if you come to think about just about any dimensional properties of engineering is a combination of those things, such as think about, what is the velocity? Velocity is length over time, isn't it? What is acceleration? Acceleration is length over time square, right? Stuff like that. So you can combine all of those basic dimensions to create an actual unit of a property of engineering. And then, as I say so, force is actually a made-up unit, as you can see. Force is a made up out of those 3 plus 1 basic dimensions. Okay. So as much as you love SI unit, there's a bad news, but let's talk about that later. Let's move on for a moment to next page, okay? Let's just take a look at US customer unit because everybody hates this. I'm going to tell you the source of the hatred of this unit system, okay? So let's just talk about three base dimensions. Mass and length and time. Let's for a moment, just forget about the temperature, but so suppose if you choose a standard dimension of unit of mass, actually, let's just do it later. Let's just choose easy one to begin with. Let's just choose the standard unit you appoint for US customary units for time. What is the standard unit of time? Standard. It's a second. People don't use minutes or hour or 1 week as a standard unit. In other words, standard in terms of, okay, I'm going to analyze an engineering problem. The problem is given in terms of minutes. Let's say shaft rotation revolution per minute. Can I pick up a value associated with that unit, 60 RPM? Okay, that's 60. Can I just pick up that value and punch that value into my calculator together with other values? Let's say, suppose if you try to determine how much torque do I have, the problem is given, okay, shaft diameter is 2 feet, I don't know. And then rotation is 60 RPM. How much torque do you need to have? Or how much torque you develop in, I don't know, pound foot. So all of those numbers are associated with those different units. What is the standard unit you want to have for that computation? It's a second. So if the RPM is given, what do you need to be doing? RPM is not the standard unit. You have to convert it to revolution per second, not the minute. So the number, original number could be a 60, but it's going to be a different number. That different number, you need to get that first. then use that number in your calculator. Do you understand what I'm talking about? That's the standard unit. Important concept in your computation. Okay. Standard unit. So here's quite important. When you compute something, you have to stick with standard unit. You have to convert whatever the original unit's given, convert it to standard unit, and then pick up that number inside of your calculator to compute. That's what you need to be doing, and there's absolutely no exception for that. Let me repeat, there's absolutely no exception. You have to do that. You have to compute based on standard unit. Standard unit is oftentimes called coherent unit. Coherent means if you stick with seconds for the times standard unit, it is going to stick with other standard units very nicely so that you can create a product such as, for example, force. Force is made up, like I said. Force unit as a standard, 1 pound of force is combined with those other units, okay? In order to create the standard unit of force, you have to stick with those other standard units of mass and length time. So let's begin with easy one. What is the standard unit of time? It's a second. And then now this is something you really hate in US customary unit. What is the standard unit of length? Anybody?
The foot.
Do you like that? That's your standard unit.
No, I mean like feet, like FT.
Yeah, this is a standard unit. And then this is a standard unit, and it seems too big. Lots of people, actually, especially, like people in machine shop, they don't like this unit because it seems too big to represent certain things. So people use something else. I'm going to switch to the red font, okay? So people use this unit instead of foot all the time, almost all the time, especially machine shop. What is that unit? And people like that unit so much, so oftentimes people say, oh, this is the standard unit. What are you talking about kind of attitude? What is that unit? You use this all inches. Now I'm using red font and then question mark of inches because inches are quite often used almost as if this is a standard unit of the ranks. But this is not the standard unit in engineering. That's one of the confusion that actually comes in first. Okay, so people hate SI, well, people hate US customer unit because the standard is foot, which is this. This is 1 foot. Suppose if you have a 2 feet, what do you have? It's going to be 2. If it's 2, it's a feet. If it's 1, it's a foot. You have to differentiate. Well, people hate that. How about 1.5? I don't know. Let's use FT. Anyways, this is standard. And people don't use it as if it is standard. Let's be careful. People use inches all the time instead of foot because it's so much more convenient. But be careful, you cannot use the value associated with inches inside of your calculator, period, because it's not standard. Okay. Very, very funny one. What is the standard unit for the mass for US customary unit? Please volunteer, your comments welcomed. Do you know the
Is it the slug?
Yeah. So you are saying, okay, thank you for your volunteer. So you're saying this? This is the slug, right? Then you go like slug. So this is honestly my response when I first came to the United States, taking statics. And then I heard about, okay, standard unit of mass is slug. Ah, what the hell? Slug? Never heard of it. Never use it. Slug? Why this is standard? Slug, in my opinion, is, oh, this is slug. Okay. Have you ever used slug in Walmart? Can I have 2 slugs of that apple, please? No one understands it, right? So have you ever wondered why this is standard unit for mass? And people use something else all the time. What is it?
Pounds.
Pounds. That's right. So this is a source of big confusion. Pounds, mass. People use pounds in the meaning of mass. And they have a unit also, pound mass, LBM. People use pound mass quite often, so that almost as if, hey, this is a standard, we never use slug kind of attitude sometimes. But in engineering, slug is standard. Okay? So now you're getting kind of confused. So another confusion come in. So, okay. Where am I now? So let me use this space to explain something, okay? So remember, weight, which is a weight is a force, okay? This is a made-up unit. Something called combined. Combined combined property. How's that? Combined property. Force equal to mass times acceleration, or weight is equal to mass times acceleration. Now acceleration happens to be a gravity. That's called the weight. Okay, so it's basically combined with mass times acceleration. Acceleration is length over time square. So this is combined with mass multiplied by length divided by time square. Okay? So this must be made up with standard units associated with each. Now, like I said, standard unit of mass is slug. Oh, okay, slug. Yeah, multiply by standard unit of length. What's that? Foot. Huh? Okay, slug times foot. What is the standard unit of time? Oh, that's second square. Okay, so this is the unit of force. And then somebody said, well, let's define this as a new unit. This is Newton. Okay, so this is, somebody said, oh, let's call this 1 Newton. 1 Newton is 1 slug multiplied by 1 foot divided by 1 second square. That's essentially 1 Newton. This is made up unit combined with mass, length, and time. Okay, so your confusion gets into play. That means if you keep using pounds mass for mass unit, you can't use pounds mass. Oh, you have to convert it. Okay. Conversion. One slug. 32.2 pound mass. Yeah, that's right. This is a unit conversion. You've been using pound mass for mass. No, you can't use that. You have to convert it back to slug. Slug is a standard. You have to convert it. Okay? Or you've been using inches. No, it's not acceptable. You have to convert it to foot. 1 foot is 12 inch. So this is a very, very important unit conversion. Almost all the time you have to do it before you punch your calculator. Whatever the value given in pound mass need to be converted to slug. Inches need to be converted to foot. And then, of course, if you're using minutes for your time, you have to convert it to second. And use all of those conversions first. And then after that, you're going to compute. And then here we go. You can compute the proper force with the standard unit of Newton. Okay? Now come to think about, wait a minute, it's not Newton. What I'm talking about. Newton is SI, isn't it? What is this, by the way? This is a pound force. Okay, sorry about that. Pound force. Pound force. Pound force? Pound force. Is it different from pound mass? Anybody?
Yes, sir.
It is different. One is mass. One is force. It is different. Pound force is a standard. Pound mass is not the standard. Okay, you get confused? Okay, so let's just okay, let's just summarize what we just looked at. Mass is a slug. This is a standard. So if you stick with foot and second and slug, mass ranks times standard unit, you're going to create the standard force unit, which is pound force. Pound is a pound force. So this is optional. If you use pound as a meaning of pound force, this is a standard use of pounds. So oftentimes people put the subscript F indicating this is pound force. That's okay, but it's optional. If you simply say pound, this is automatically taken as a meaning of pound force. Okay? If you use pound as a meaning of mass, okay, it's a non-standard use of pounds. Subscript M is required, not optional. You have to always put the subscript M. Okay. Okay, so far. You got confused, right? So let's just go back to SI unit because that's much easier as you think. I'm not sure about that, but let's just go back to a standard unit of SI, okay? Most of the time people think this is so much nicer. Is it true? Let's take a look. So mass ranks time, okay? What is the standard unit of mass?
Kilograms?
Kilograms. Kilogram. That's quite important. But let's be careful. Kilogram is essentially 1,000 gram. And then happen to be kilogram is chosen, not the gram. Okay. I think the majority of a question comes in why kilogram is chosen over gram is because this is so much easier choice. Most of the times, if you choose gram to represent, such as, okay, what is your mass of your car in grams? It's like a huge number. Kilogram is so much easier. So it's going to be like a 20 kilogram versus 20,000 gram. No one wants to carry like a 20,000 all the time in a calculator. So kilogram, okay? What is the standard unit for rings?
Meters.
It's 1 meter. So I was born and raised in SI unit country, so I can tell, okay, well, 1 meter, that's much, you can say that. Anyways, second is a second for the time. Okay? So as you can see, meter, kilogram, and second, those are the standard units. So let's just think about force, okay? This is made up, like I said, mass times acceleration, mass times length divided by time square. So if you stick with all standard units, mass is a kilogram, length is a meter, divided by second square. So similar token, okay, people decided, okay, let's define this. This is a Newton. Okay. So 1 Newton is created by 1 kilogram of mass multiplied by 1 meter divided by 1 second squared. That's 1 Newton of force. Okay. Okay, so far. So compared against US customer unit, this seems so much easier. Do you think so? Do you agree? Can you react? Oh, this is so much nicer. I love SI unit. Please react. Do you think so? Okay, anyways. So let's just revisit US customer unit. There are so many confusion, source of confusion. One of them is, of course, pounds mass, which is non-standard, and pound force, which is the standard. Let me just use a green marker. This is a standard. Pound force is a standard. Pounds mass is a non-standard. And 1 foot is standard, not inches, but the people use inches all the time. So there's a sort of in your mind, okay, as an engineer, you have to differentiate yourself with the rest of the world. You know, people outside of the engineering classroom says, "Well, inches are standard. I always use inches. In my machine shop, inches are standard unit." Your engineer basically says that, I understand that. That's the unit you usually use because it's most convenient for your own applications. But in engineering unit system, that is not the standard unit. I have to convert always inches back into foot in my analysis. Okay. Also another thing, pounds mass and pound force confusion. Like I said, 5 pounds of apple. Take it to the drugstore saying, is this 5 pound mass or 5 pound force? Which one is it? And then the answer is, I don't care. Pounds are pounds. What are you talking about? That's probably the response that you receive. Okay. But you're an engineer, right? Especially if you're astrotrack. You're astrotrack engineer, right? That's not your attitude. You're basically saying that, well, it's important because if you take this back to the moon, it is going to be different. Okay. If you say this is 5 pound mass, if you take it to the moon, how much pound mass do you have? Anybody? Actually, 6 pound mass. Okay. Let's say if this is a 6 pound mass of an apple, if you take it to the moon, how much pound mass do you have?
Same.
Same.
You would have
Same. It never change because mass is a mass. But if you say this is 6 pound force of an apple, if you take it to the moon, how much pound force are you going to have?
you would have 1 pound apple.
1 pound force on moon. Pound mass and pound force are not the same thing, fundamentally speaking. However, as long as you are on Earth, it's the same value. Well, that's the point. Okay, let me just demonstrate here. So weight is a force. This is mass times gravity. Acceleration now becomes gravity. Gravity, you know that. So now you say, okay, let me demonstrate it here. Now say, oh, okay, fine. You say this is 5-pound mass. I'll take it. You say this is 5-pound mass, right? Then customer service rep said, yeah, fine. You can take it away. Then 5-pound mass is not the standard unit, you know. So let's just convert it. Okay, let's convert it to slug. Okay, one slug is 32.2 pound mass, right? So this is going to make a slug of a mass. Let's multiply by gravity on Earth, standard sea level gravity, 32.2 feet per second square. Is going to get you the weight, how much? How much?
5.
5, what's the unit?
Pounds for
Pounds force. 5-pound force. So now you all of a sudden realize that, okay, so 5-pound mass creates 5-pound force of weight if you are on Earth's standard gravity. Okay? So if you go to the moon, what happens? The gravity all of a sudden becomes 1/6. So this 5-pound mass becomes 1/6 of 5-pound of force. Okay? So those are different values. So this actually happens only if you are under the standard gravity on Earth. This is called gravitational unit system. Okay? This is very, very, very important concept. Do not mix up pound mass and pound force in any of the engineering class. Okay? People still do that. Now, as long as I teach engineering class, just about any class, I'm not going to allow you to mix up pound mass and pound force. Okay? If you use pound mass, subscript is always required. If you use pound force, it's optional. One is standard use of pounds. One is non-standard use of pounds. And inches seems like standard unit, but don't use inches in your calculation. You always use feet in your calculation. Somebody said something. Go ahead, please. Did you have a question or something? I think I heard somebody say something.
No, my mic just went off. Sorry.
Oh, it's okay. No problem. So I hope this is understandable for you. Very, very important concept. Please raise your hand if it makes sense. Good, good, good. Appreciate that. Okay, everybody. That's great. So this is something like you have to be extra cautious when you use a U.S. standard unit system. However, let me tell you something. I'm from SI unit country. Do you think SI is such a super nice unit, so you always want to stick with? No. The hell no. SI unit is also very confusing. Okay? You can try this one simple thing to find out how confusing SI unit could be. You go to fish market and then try to buy a fish in SI unit country. Let's say Japan. You know, fish market. You go to fish market. Okay, try to buy fish. It's easy. No, it's not easy. Because you say the weight or force is a weight. The standard unit of the force is Newton, right? So try this. You go to fish market and grab someone, a fisherman or somebody saying, hey, can I have 2 newtons of fish, please? May not necessarily be in English. You can use foreign language and say, well, can I have 2 newtons of fish, please? Then that person says, what again? 2 newtons. What the hell is Newton? I've never heard of it. Never use it here. Okay. Let's say you pick up a health meter scale. You want to measure your weight this morning. Turn on to SI unit mode. What is the unit comes up? Newton? Oh, this morning I have 700 newtons. Huh?
It's kilogram.
Kilograms. People use kilograms. Kilograms for the meaning of weight. What is that? Kilogram force. Let me just use a red marker. Mass or force. So oftentimes people use kilogram meaning force. kgf. This is called kilogram force. Okay? People use that always, casually use it. Now, engineers, aerospace engineers in France, SNECMA, they use thrust of an engine, like 5,000 kilograms of thrust. What the hell? What are you talking about? It's engine thrust, isn't it? Yeah, 5,000 kilograms. Huh? Kilogram force. This is always used. Very confusing, okay? So once again, you have a unit conversion of a kilogram force right here. So once you see that, 1 kgf is equal to 9.81 Newton. You have to convert it. So this is a unit conversion. Whenever you see people use kilogram indicating this is a kilogram of a weight, you have to convert it to Newton because Newton, although nobody uses it, it's a standard unit. Engineers, you are the only one using Newton, but who cares? You have to use Newtons. You cannot use kilogram force just like everybody else outside of the engineering classroom. You are an engineer, you have to differentiate yourself from the rest of the world. This is one step. People casually use kilogram always. No matter where you go, people use kilogram as a weight or force unit. It's not the standard at all. You have to convert it to Newton. Similar to this. Who the hell uses slug as a unit of mass? You are the only one. Okay? But you have to use it. People use pound mass, but you have to use slug. This is a standard. Okay? This is a standard. Okay? Why is that? It's the same reason. Okay? So, same reason. Remember, 5-pound mass of an apple with 5-pound force under the standard gravity of Earth. It's the same meaning. So if you go to fish market and you can argue with a fisherman saying, oh, you say 2 kilograms of fish. Is it the kilogram force or kilogram mass? Which one is it? Huh? Kilogram is a kilogram. Well, no, I want to know. 2 kilogram mass you're talking about or 2 kilogram force you're talking about? Which one is it? Kilograms are kilograms. What are you talking about? Okay, well, I'll take it kilogram force. How's that? Sure, fine. Take it. All right? So you say, okay, I took it as 2 kilogram of force. 2 kgf. Then you quickly realize, well, wait a minute, this is not standard unit. I have to convert it to standard unit Newton. So 1 kgf is 9.81 Newton. Here we go. Let's multiply this with the standard gravity 9.81 meter per second square. Okay, so this is the mass in Newton. This is acceleration or gravity in meter per second squared. So this is going to, actually, no, what I'm talking about. This is force, isn't it? Sorry about that. Forget about what I just said. Let's just do an easy route. Okay. Easy route. Okay, so you keep arguing. Okay, so this is 2 kilogram force or 2 kilogram mass. Which one is it? I want to know. Can I take it 2 kilogram mass? Huh? Then you say, well, sure, fine. Go ahead. Do it. You're crazy. Okay. Well, I take it 2 kilogram mass of fish. 2 kilogram mass of fish. All right. This is a mass. 2 kilogram. Oh, kilogram is a standard unit of mass. I can use it as is. Okay, let's multiply it with 9.81 meter per second of gravity, because this is on us. This is going to give you the weight. So this is, oh my goodness, I need a calculator. Wow. Okay, so, okay, 2 times 9.81. It's 1962. What's the unit? Anybody?
In Newton.
This is Newton. Oh, okay. So you're talking about 1962 newtons of fish. What's Newton anyways? Okay, well, let me convert it. 1962 Newton. Let's convert it to kilogram force, because 1 kilogram force is 9.81 Newton. How much kilogram force do you have? Anybody?
Two.
2 kilogram force. Then you go argue back and say, oh, you're talking about 2 kilogram force of fish. Yeah. 2 kilogram is 2 kilogram. What are you talking about? But be careful about that. This works only on the surface of the Earth, right? If you go to moon and argue with a fisherman on moon, well, you have to seriously argue about, is this a kilogram mass or a kilogram force? Because those two are different values. Do you understand that? This works only if the gravity is standard sea level. If you go to moon, this is going to be 1/6. So what happens? This is no longer 2 kilogram force of fish. Or actually, 2 kilogram mass of fish on moon will become 1/6 of a 2 kilogram force. Okay. Obviously, 1/6 of a 19.62 Newton. So weight and mass are different, but oftentimes we use the kilogram, meaning you can apply both kilogram mass or kilogram force, because numerically speaking, those are the same value under the standard gravity. This is the concept of gravitational unit system. Okay? This is probably one of the most important things at the early stage of engineering. People do not understand gravitational unit system, will make a devastating mistake without realizing. Okay, what is the good example of this kind of mistake? Apollo 13. You know, pound mass, pound force mixed up, kilogram force mixed up. This actually happens. One of the accident at the Thunderbirds. Okay, oops, about 5 more minutes to go. You know, one of those terrible mistakes happened in the past is associated with this poor understanding of unit system. As an engineering major, I'm not gonna tolerate misunderstanding of units. You have to master it. You have to master it at the early stage. That means today. Okay, so today's lecture is very important. Okay, so that's all about unit system. So let's just stop here today. So tomorrow I'm going to, once again, I apologize. I have to do online remote lecture tomorrow too. So in-class lecture is going to start on Monday next week. So tomorrow we are going to cover page 5, section 1, 2, scalars and vectors. Okay, so let's just stop here today. Do you have any question?
What was the on the? I think the it is on page 3. The L over T and L over T squared. What are those again?
Yeah. Okay. So this is velocity.
Okay.
Yeah, velocity is like a meter per second. So this is length over time. So this is acceleration.
Gotcha. Thank you.
Yeah, you're welcome. I appreciate that question. Any other question? Okay, have a wonderful day today and then see you back tomorrow.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
See ya.